we will next look into a new topic which is known as data converters. Now, as we know that any digital system that we are designing, so ultimately it is going to be used in the environment where it has to interact with the analog signals. Like if we are looking into say a temperature controlling system, so the temperature is an analog value and there are sensors which will be sensing the temperature, and that sensing will convert the physical signal into some electrical signal. So, it may be converting the temperature value into some current or voltage value, but that is an analog value. But in case of these computers that we have, so they can process only digital value. So, we have to convert it into some digital value. So, that way there may be some error introduced in the process, like maybe when the temperature is 40 degrees Celsius, so it outputs some voltage. So, if it is expected that say if from 40 to 45, so the next temperature sense is 45. So, accordingly the voltage value increases. So, then that conversion to digital from this voltage to this digital value, so that should be equivalent to if we are going from say 20 to 25 degree change. So, the amount of 5 degree change that we have, the corresponding if the sensor that we have, so it gives a good reflection of it in terms of analog signal, analog voltage, and if we assume that the analog signal change is equivalent to the change in the physical signal, then from this analog signal to digital signal conversion, that should also be proportional. So, we need to have some special circuitry that will be doing this conversion of data, like when the computer wants to read some analog value from the environment. So, it has to be some it has to be converted from analog to digital. Similarly, if the computer wants to control some system, so by giving some electrical signal to, so for example, some motor has to be rotated. So, motor has to be given some voltage with which it will understand how, at which speed it has to rotate. But this computer cannot output the voltage directly, so analog voltage directly. So, it will output some digital value, and then that digital value has to be converted into analog signal before giving it to the motor. So, this type of data converters are necessary when we are interfacing a digital system with the environment. So, in this part of the course, so we will be looking into two such converter mechanism. One is called digital to analog converter or DAC, and another is known as analog to digital converter or ADC. So, we can say that a typical diagram for this entire system is like this, that we have got this as the digital system. So, this is the digital system that we have, and from the outside world, so we are getting the analog signal, signal, and it passes through something called analog to digital converter. So, this is the ADC, and then this value is the digital. So, this is the digital value that we have, and here we have got the analog value. And after doing the processing, this digital system, it outputs some digital value, and that digital value has to be converted to analog before it is given to the environment. So, this is one digital to analog converter, and then this is the analog signal. So, this is the analog signal that we get. Okay. So, this is how this whole system will work. Okay. So, we need to understand these two circuitries, this DAC circuitry and ADC circuitry, because they becomes a very important part of this interfacing this digital system to the analog environment. So, how do we do that? So, that we will see. Now, the first there are two distinct type of converter. So, we will first look into the digital to analog converter, so which will convert the digital signal to the analog output. So, what is DAC? A digital to analog converter, it converts a digital signal to an analog voltage or current output. So, because voltage and current, they do not cause much of problem, because if we get a current output also, so we can pass it through a resistance and then measure it the corresponding voltage. So, as a result, this current and voltage, so these two outputs, any of these outputs are okay with us. So, if you give some, so if this is the digital to analog converter block and you are giving an input like say 100, 101 etc., some bit pattern is fed. So, it is expected that it will be outputting some analog signal. So, it may be some for the sake of understanding. So, I have drawn a sinusoidal signal here, but it may be it is definitely dependent on the bit pattern that you are feeding here. Accordingly, you can generate some analog signal this point. Of course, you can feed this bit pattern in such a fashion that the output signal is a sinusoidal signal or a square signal or a triangular signal, whatever we want. So, whatever control signal is needed for controlling the device that is connected to this analog signal. So, we can produce that signal accordingly. So, this is the digital input signal. So, that maybe we are outputting from 0000 to 1011, and on the analog output signal. So, it increases like this. So, when it is 0000, so output is also 0. When the input is 0001, so output is this much, 0010 output is this much. So, this is the behavior of the DAC. So, at these count values 0000, 0001, 0010, so it will be outputting these corresponding voltages. Of course, it is not a continuous signal, because in between what happens. So, these points are not known. So, this is basically by means of some approximation, we can visualize it as a continuous signal like that. Now, if you look into these types of this digital to analog converters, so there are many types of DACs that are available, and they are usually switches, resistances and operational amplifiers. They are used to do this conversion. And there are we will be looking into two types of DAC. One is known as binary weighted resistor and R2R ladder type resistor. Okay. So, as I said that the main components of a DAC, they are switches, resistances and some operational amplifiers. They will be used for getting the analog output. The first digital to analog converter that we will look into is the binary weighted resistor based digital to analog converter. So, it utilizes a summing operational amplifier circuitry. So, what we mean by a summing operational amplifier is, so operational amplifier is some circuit like this. I hope you are familiar with this diagram. So, basically some input is given, it takes a differential input and this amplifier has got a gain of A. So, what is the difference between these two voltages? If we call it V diff, then the output is A into V diff. So, ideal operational amplifier, this A is infinity. So, this value will go to infinity. So, if on the other hand we can have some feedback to control the gain. And as you know that there are two types of organizations of this amplifier for using op amp. So, one is called inverting amplifier, another is called non-inverting amplifier. So, this they have got particular gain expression which is less than infinity. For example, if we are having this inverting type operational amplifier, so the circuit diagram is like this. So, if we apply V in here, and then if this resistance is say R1 and this resistance is say R2, then this V out value is given by minus of R2 by R1 into V in. So, from this infinity gain, so we can restrict, we can control this gain of the circuit. Now, this type of so if I have got a number of voltage sources, so V in 1, then V in 2, V in 3 like that. So, they can be added here, the successive terms can be added here, and then it gives rise to something called this summing operational amplifier. So, we will see some circuitry on that. However, so these weighted resistors are used to distinguish each bit from the most significant to the least significant bit. So, each bit will contribute to some value for into the output. So, most significant bit, its contribution will be high, that is if the most significant bit is 1. So, it will contribute significantly to the output voltage or current. So, if you go down and look into the successive bits, their contribution will be lesser and lesser. So, the least significant bit, it will have the minimum contribution and that way it will go. So, transistors are used to switch between Vref and ground, which is bit high and low. So, Vref is the reference voltage which is taken as this high value, and low is the ground. So, that is taken as the 0 value. So, this is the structure you can say. So, each of these bits that we have, so each of these lines, so they constitute one bit, fine. So, you can see that we have got this operational amplifier where this bit. So, if it is so this bit, so if I connect it to this point, so this Vref, the current that is drawn by this is Vref divided by R. So, similarly, when this switch is connected to say this point, then the current drawn will be Vref divided by 2R. So, as a result, the contribution from the first if this switch is connected here, then the contribution that is coming onto this line is the current value is Vref divided by R. And if we connect this line to here, if it is connected like this, then the contribution is Vref divided by 2R. So, this contribution is less than this one. Okay. So, as you go down and down, so what happens is that this contribution becomes exponentially less. So, whatever be the contribution here, current contribution, so this has got half of that, this has got half of that. Finally, the nth bit, it will have the component, the contribution reduced by a factor of 2 to the power n. So, if we assume this operational amplifier to be an ideal operational amplifier, so no current flows into this op amp. So, whatever current comes like this, it passes like this, fine. So, you can say that V out is given by I into RF. So, V out is given by I into RF. So, we can try to figure out what is the value of I, and based on that we can find out what is the voltage that is coming as the output. So, let us see. So, this I, as I was telling, this I into RF. So, this expression for I, so it has got this V 1 by R for the most significant bit, V 2 by 2. V 1 is the most significant bit. So, it is the and V n is the least significant bit. So, whatever be coming here as voltage, so this is given by V 1 by R. So, at this point if the voltage is V 1, so it is V 1 by R, second one is V 2, so it is getting V 2 by 2 R, then third one is V 3, so V 3 by 4 R, last one if it is V n, so V n by 2 to the power n minus 1 into R. So, this is so this way it is reduced. So, this should be 2 to the power n R, not 2 to the power n minus R, n minus 1. So, this is yeah. So, there are n such cases. So, it is like this. So, V n is the least significant bit, and then it is V n divided by 2 to the power n into R. Now, if we so if RF equal to say R by 2, so if we take RF equal to R by 2, then this V out equal to minus I into RF. So, which is V 1 by 2 plus V 2 by 2 plus V 3 by 8 up to V n by 2 to the power n. So, then we can say that this if we have got say 4 bit converter, then this V 1 is nothing but Vref, this V 1, V 2, V 3. So, they are all equal to Vref. So, this Vref is taken out. Now, depending upon this B 3, B 2, B 1 and B 0, this bit pattern, so this contribution will be coming. So, you can say in this diagram you see that if I connect this point to here, then V 2 becomes equal to 0. If I connect this point here, then the V 2 becomes equal to Vref. Okay. So, that way we can say that this V 1, V 2, these voltages can be either equal to Vref or equal to 0, and that is controlled by the position of this switch. So, when the switch is connected to this, we can say that the corresponding bit is equal to 1, and when the switch is connected to this position, so we can say the corresponding bit is equal to 0. So, here if I take say B 3 equal to 1, that is the most significant bit is connected to is equal to 1. So, it is getting the contribution Vref V 1 equal to Vref in that case. So, in the second one, if B 2 is not second bit is not connected. So, B 2 is second bit is second switch is connected to ground. So, that means B 2 is equal to 0. So, in that situation, this B 2 being equal to 0. So, Vref contribution does not have anything to here V 2 becomes equal to 0. So, because of this B 2 into V ref, so B 2 being equal to 0. So, this the value of V 2 becomes equal to 0. Similarly, if the third bit is equal to 1, then this V 3 becomes again equal to V ref, and if this nth, so if the least significant bit B 0 is equal to 0, then this contribution V 4, so that will become equal to 0. So, B 3 corresponds to bit 3, B 2 corresponds to bit 2, like that. So, that way we can have a binary weighted resistor based structure for getting this V out. So, depending upon the digital value that you feed in B 0, B 1, B 2, B 3, the value of V out will get determined. So, what are the advantages? So, it is a simple construction and analysis. So, simple because you just need a couple of resistances and then connect it in some fashion. Conversion process is quite fast because it is all the comparisons are being done simultaneously. So, the conversion process is also fast, but there are disadvantages because requires large range of resistors like for 12 bit DAC. So, for 12 bit DAC, so you can understand if you look into this diagram. So, this is going from so it is going from R, 2R, 4R up to 2 to the power 12 R. Okay. So, 2 to the power 12 is 4096 R. So, if you take even if you take R equal to 1, okay, if you take R equal to 1, then this is equal to 2. So, this is equal to 4. So, you need all these resistors like 1 ohm resistor, 2 ohm resistor, 4 ohm resistor. So, like that up to 4096 ohm resistors. So, getting resistances of this exact values is a problem, or getting resistances in this ratio is also a problem. So, that makes it difficult for this realization of this binary weighted DAC. So, with necessary high precision of low resistor, so it is difficult. Requires low switch resistances in transistors. So, these transistors that we have taken, so this resistance is actually coming. So, these switches they are actually realized by some transistors, like if it is a MOS transistor. So, this is the connection is like this. So, this point is connected to V ref, this is connected to ground, and we have got a switch. So, this is connected to the digital bit B. So, if B equal to 1, then V ref gets connected here. If V ref B equal to 0, then this ground gets connected here. So, the problem is that this channel resistance that also comes in the series with the resistor. So, here I have got that R resistor. Okay, this is the R resistor finally going to this side and finally going to that op amp. So, this channel resistances they will come in series with this R resistance. So, with this channel resistances should also be pretty low, so that we do not have problem in getting the proper resistance values implemented. So, that is the point. So, this switch resistances should be low, and it can be expensive because of this getting these resistances of good precision, particularly the resistors which have got low values, getting them with good high precision may be costly. Therefore, so it is usually limited to 8 bit resolution, you do not go for 12 bit and all. So, you normally keep it within 8 bit resolution. Another type of DAC which is pretty common, which is known as R2R ladder. So, here you need only two types of resistors, one is of value R, other is of value 2R. So, unlike the previous case where you are requiring a series of resistance values, so here that is not required. So, you require R2R ladder type of R and 2R resistances, and they are connected in this fashion. So, from V ref we make it R and finally there is a resistor 2R. And so, this is a 4 bit converter. So, we have got 3 such resistance R in series and then a 2R resistor in series, and then from this point. So, we take the 2R resistance and take it down. Now, this depending upon the bit configuration. So, either this is connected to ground, or it is connected to this one, so this point which is it may be connected to this point or it may be connected to ground. So, this switch, so either it is connected here. So, this sorry. So, this point, so it is either connected to this or it is connected to this. So, when it is connected to this, that means a 0 is coming here. If it is connected to this, then the contribution, the current flow contribution actually so either the connection is like this or the connection is like this. So, if it is connected like this, then there is no contribution of this bit, and if it is connected like this, then it is this current flows in this fashion. Similarly, for the second bit, maybe it is connected like this. So, as a result, this does not have any contribution, no current contribution is coming, but if it is connected in this fashion, then again a current contribution like this will come. So, then it is a summing type of structure. So, that is all right. So, each bit corresponds to a switch. If the bit is high, the corresponding switch is connected to the inverting input of the operational amplifier. If the bit is low, the corresponding switch is connected to the ground. Okay. So, it is in this fashion it is connected. Okay. So, this is the switch. So, either it is connected to the inverting input of the op amp like this, or it is connected, if the bit is low, then it is connected, this switch is connected to the ground. So, this way this connection is made. Now, so let us see how it works, fine. So, so if you look into say this part, then what is happening is that this V3 voltage, so there is a 2R, so these two resistances are there, so they are in parallel. So, R equivalent is equal to R for this part. So, the equivalent, so when this bit is connected like this, so some part of the current will flow like this, some part of the current will flow like this. So, you will get R equivalent equal to R. So, now, now if you consider this V2, okay. So, V2, after that we have got this R, then V3, then this part is equivalent to R as we have seen previously. So, this part is equivalent to R. So, this equivalent, so the V3 becomes half of V2. So, V3 is equal to half of V2. In this way, if you continue, then V2 will turn out to be half of V1, V1 will turn out to be half of Vref, and V out is equal to minus I into R. So, that is there. So, once you have got these values of V1, V2 and V3, so you can find out what is the value of I, and accordingly you can get the V out value. So, for example, in this case so we have got V3 equal to 1/8 of Vref. So, so V1 is half of Vref. So, V1 is half of Vref, V2 is half of V1, that is 1/4 of Vref, and V3 is half of V2, that is 1/8 of Vref. So, this way we get it like this, and then when this summing is done, then it becomes minus R into B3 into Vref by 2R, okay, plus the B2 into Vref by 4R, plus B1 into Vref by 8R, plus B0 into Vref by 16R. So, by taking this R equal to this feedback equal to half of R by 2. So, in this structure, so it is assumed that this feedback resistance, this RF equal to R by 2. That is why this expression becomes like this. Okay. So, B3 is connected to so B3 is connected to bit 3, B2 is bit 2, etc. So, if bit n is set, then Bn equal to 1, and if bit n is cleared, then Bn equal to 0. So, in this fashion we can have an R2R ladder implemented, and it gives the corresponding digital output. So, we have got this V out, this is the final expression that we have. So, Vref into B3 into 1 by 2. So, this taking that Rf equal to R by 2. So, we get it Vref equal to B3 into 1 by 2 plus B2 into 1 by 4, B1 into 1 by 8 plus B0 into 1 by 16. So, for general n bit R2R ladder and or binary weighted resistor DAC. So, the equation becomes V out equal to minus V ref into sigma I equal to 1 to n B n minus I into 1 upon 2 to the power I. So, this is the final expression for any DAC circuitry that we have, which converts from digital to analog value. So, why you should go for R2R ladder? So, advantage is the only two resistor values are necessary, which is R and 2R, and does not require high precision resistors. So, only thing is that you need so if for getting 2R, so what we can do, we can take one resistance and one type of resistance and connect two of them in series. So, we get 2R. So, ideally you can say only one single resistance is sufficient, and you can just sometimes connect two of them, sometimes connect one of them to get the R2R configuration, or you can get the exactly double of the resistance 1K and 2K, and that way you can connect it. So, disadvantage is the low conversion speed than binary weighted DAC, because of this current this voltage being decided by individual resistances, and then so it becomes slower compared to this binary weighted DAC. When you are talking about specification of a DAC, now there are several DACs that may be available in the market. Like if you are looking for a particular type of DAC, so what are the factors that you should talk about? One thing is the resolution, then the speed, then resolution will come to this term, then speed of conversion, then how much linear it is, then the settling time, reference voltage and error. So, you look into these issues. Then resolution, it says the smallest analog increment corresponding to 1 LSB change. So, the minimum amount of change that a DAC can do is by changing the LSB. So, if you change the least significant bit from 1 to 0 or 0 to 1, there will either be increase or decrease in the analog output. So, when you do this change, then what is the corresponding analog voltage change? So, that is the resolution. So, that you cannot change the analog voltage by a value which is less than this one. So, that is the resolution. N bit resolution can resolve 2 to the power n distinct analog levels, and so basically from one bit one say bit sequence to the next bit sequence, next digital count binary sequence, if you go, then what is the minimum change in the analog voltage? So, you cannot go change beyond that. So, so if you have got the reference voltage as Vref, then you know that there are 2 to the power n distinct analog levels that you can have. So, the resolution is given by Vref divided by 2 to the power n. So, which is also known as the voltage corresponding to LSB change or VLSB. So, this is the expression for the resolution of the DAC, where n is the number of bits. So, common DACs, they have got 8 to 16 bit of resolution, because for higher resolution, so I have to go for more number of bits, and then the construction of the DAC becomes difficult. So, normal DACs will go for 8 to 16 bit of resolution, and depending upon the Vref, you can get the final analog voltage value by which it can change.